Okay, welcome to the second lecture on mechanics of materials. So the second lecture focuses on the elongation through axial loads. So when you apply forces to something, the length of it become more. How about if I have a composition of different forces in a place, or where we have a change of different forces? So let me just to give you a quick example. In this example, I apply force in different location, and I want to see how much elongation from A to D is, right? So if you consider every section of it, there's a little force on there. Now, some forces, they act like they actually create a force and make it elongated. Some of them, they become compressive forces. Now, what we did in the first session, we discussed that majority of material, they act like a spring in their elastic region. Then we can use the Hooke's law, which is going to say sigma is equal to E epsilon. Like a reminder, sigma is a stress, epsilon is strain or elongation. Now, if we use, instead of in this equation, instead of sigma, if I use F over A, and instead of epsilon, I use delta over L. I'm going to be ending up into the equation of sigma is equal to FL over AE. And here visually I show you that the length is the length of the specimen, the force that we apply. We're going to get to this equation that delta, the elongation here, is equal to FL over AE. If we have many delta, we can say that sum of FL over AE, right? So what do I mean? I mean that in this example, the question asks me to find delta AD. So if I want to find delta AD, I need to find a stretch or compression in every part. So in the part LAB, I need to find how much I have the force here, how much elongation at the part AB is. Then moving on to part BC, same thing. I need to find how much elongation is, how much force is, and then CD. So basically I can say delta AD is equal to delta AB plus delta BC plus delta CD. And then from there I get to this equation FAB LAB over AE. Again, in this case, why I use AB? Because that's the same material, so E stay the same and same cross-sectional area. So they are given to me. E is 200 gigapascal and area as 200 millimeters square. So these two were already given to me, and I'm going to use them in my equation. The E and A were already given. So let's start working. So now what I do, the first thing I do, I draw the force diagram, knowing how much the force in every of those sections are. So how I got to this diagram? I get to know that FAB is 5, FBC is minus 3, and FCD is minus 7. So I'm gonna go over it quickly to show you how I got it. So I have 3 cuts, one cut here, and one cut at the end. So on the first cut, which is going to be, this is going to be the cut for AB. That was A. The B was somewhere here, right? And then we cut it from here. We say that if you cut it, you get a normal force down here. And the normal force, if you do sum of f of x, and we have only a force of 5, I'm going to get N is equal to 5. Normal force is 5. Moving to the second section. In the second section, I have cutting it between B and C. So we cut it from B and C. So remember, this is A here. Down here is B, and down here is C. Again, not here C. C is somewhere here, right? I'm cutting from this cross sectional, cut 2. This is cut 1. And this was cut 1, cut 2. So in the cut 2, you can see, if I write the equation, I can say 8 minus 5 plus N is equal to 0. And then from there you get N is equal to minus 3. On the third cut, so here is A, here is B, here is C. I'm cutting somewhere between C and D, right? D would be somewhere here. Now you write the equation again, you're going to get N is equal to minus 7. So actually I calculate the force along these different sections. Section 1, Section 2, and Section 3. So in order to find the delta, all I need to do a bunch of substitution. So I have the force, I have the length, I have the A, and I have the E. very good to go. The only thing that you forget, mechanics of material is about unit conversion, it's about correct unit conversion. So in this case, I have 5,000. Again, it was 5 kilonewton. I use 5,000 times 2 for FAB. The next one minus 3,000 minus 7,000. Then you can put all your answer together. In this case, if you apply the forces that you show there, it will go to a compression, and that compression, the value of that will be minus 0.225 times 10 to the power minus 3. This is meter, and then I'm going to get it in millimeter. So again, I'm going to move on to another example for axial loads. So in the other example, the question will be a little bit more, like you have to do a little bit more thinking. It's not like the other problem. In this problem, we need to look into what exactly is going on. So we have two rod on two sides. We call them two short posts, and there is a rigid beam. The word rigid is very important. Rigid is something that when you apply the force to it, it doesn't bend, it doesn't twist, it stays as solid. That's the definition of rigid. So we have the bar on the top is rigid. We apply the force 90 kilonewton on it. Now the question asks us that, again, both are AC is made of steel with the diameter of 20, and then BD made of aluminum with the diameter of 40. They give me the E for the steel and E for aluminum, the modulus of elasticity for these two. I also know their diameters. When I apply 90 kilonewton there, just go back to statics, right? You apply 90 kilonewton there, and then you have two posts. On the two posts, you have two reactions. So this is going to be F of steel, this is going to be F of aluminum, and 90. If you are super smart, you can say that, okay, if the force here, 90 is too close to this, I can just simply say that F of steel is equal to 200 over 600. Sorry, I'm going to do the other one. 400 times 600 times 90, which is going to be, let me use my calculator because my